The sky exploded, and for a brief moment, nobody could explain why. Across parts of the eastern United States, people heard a sound powerful enough to rattle windows, shake homes, and trigger emergency calls from residents convinced that something extraordinary had just happened overhead. Yet, when officials began searching for answers, the explanation was not immediately obvious. There was no major earthquake, no severe thunderstorm, no clear source that neatly fit the evidence. And that is exactly what makes this story so fascinating. In a world where satellites continuously monitor Earth, where atmospheric sensors scan the skies every second, and where advanced detection networks cover nearly every corner of the country, how can a massive explosion occur above one of the most populated regions of America and still leave behind uncertainty? That question is why you should stay with me tonight. Because what begins as a mystery about a loud noise in the sky quickly becomes a larger story about how humanity observes the world around it, how scientific investigations unfold in real time, and why some questions remain unanswered even in the age of extraordinary technology. If you enjoy these slow journeys through science, mystery, and the universe, consider gently supporting this video with a like. It helps these stories reach others who may be searching for the same sense of curiosity and wonder. Now settle and relax, and let us begin. Most people assume that when something unusual happens, an answer appears almost immediately. After all, we live in an age of remarkable observation, where the satellites watch the atmosphere from space, rather than counting sheep. Radar systems tend the skies around the clock. Seismic networks record vibrations moving through Earth. Astronomers track objects crossing the solar system. Air traffic systems monitor aircraft across enormous distances. It feels reasonable to believe that if something significant happens, someone already knows exactly what caused it. But reality is often more complicated. Scientific knowledge rarely arrives all at once. Instead, it emerges piece by piece. A witness reports what they experienced. Instruments collect data. Experts compare observations. Multiple explanations compete. Some survive scrutiny. Others do not. During that process, uncertainty exists. Sometimes for hours, sometimes for days. Tonight's story begins inside one of those rare moments of uncertainty. A powerful boom echoed across the East Coast. Thousands of people heard it. Many felt it. Some described it as an explosion. Others compared it to thunder. A few believed it sounded like something moving rapidly through the atmosphere. Yet despite the number of witnesses, the source was not immediately clear. And that is where our journey truly begins. Our goal tonight is not simply to ask what caused a loud noise. Our goal is to follow the evidence exactly as scientists, meteorologists, and monitoring networks encountered it. We will explore how observations become explanations, how modern detection systems watch the sky above us, and why the difference between what people experience and what instruments record can sometimes create surprising mysteries. Because the real story is not just the boom itself. The real story is the gap between an event and its explanation. Sometimes that gap lasts only minutes. Sometimes it lasts much longer. And sometimes it reveals something important about the limits of human knowledge. The explosions heard across the East Coast are only the beginning. The deeper mystery is what happens when the sky produces an event that briefly sits beyond immediate understanding. And as we are about to discover, that question leads somewhere far more fascinating than anyone expected. But there is a problem with everything we have discussed so far. If this was simply a loud noise in the sky, why did so many people describe feeling it rather than merely hearing it? That single detail is what transformed an unusual event into a scientific mystery. Sounds are common. Pressure waves strong enough to shake buildings across a wide region are not. When residents across multiple communities began reporting rattling windows, vibrating walls, trembling floors, and a deep shockwave rolling through their homes, investigators immediately realized they were dealing with something much larger than an ordinary atmospheric disturbance. The first major event occurred during the late afternoon, when thousands of people across portions of the East Coast suddenly experienced what many initially believed was a nearby explosion. Within minutes, social media filled with remarkably similar reports. Some witnesses described a sharp crack. Others reported a deep booming sound that seemed to travel across the landscape. Many said they felt a sudden pressure change, almost as though the atmosphere itself had briefly pushed against their homes. What made the situation unusual was the geographic distribution of those reports. People separated by dozens of miles were describing the same event at nearly the same time. That immediately suggested a source located high above the ground rather than a local incident confined to a single neighborhood. Scientists often begin these investigations with a deceptively simple question. Did the disturbance come from below or from above? The answer determines almost everything that follows. If the source originates beneath the surface, researchers examine earthquakes, fault movement, underground explosions, and geological processes. If the source originates in the atmosphere, attention shifts toward weather, aircraft, meteors, and other aerial phenomena. Modern monitoring systems are remarkably effective at distinguishing between these possibilities. Seismic stations continuously record vibrations traveling through the Earth, allowing experts to identify the unique signatures associated with different types of events. When analysts reviewed the data from the first boom, something interesting appeared. The signals did not resemble a conventional earthquake. Instead of energy radiating outward through rock from a point beneath the surface, the measurements suggested a disturbance arriving from the atmosphere. In simple terms, the evidence pointed upward rather than downward. That conclusion significantly narrowed the list of possible explanations. Severe thunderstorms can generate powerful acoustic shockwaves, but weather conditions across much of the affected region were relatively quiet. Industrial explosions generally leave physical evidence, damage, or a clearly identifiable source. Aircraft can generate sonic booms when traveling faster than the speed of sound, but such events are often linked to known flight operations. Another possibility involves meteors entering Earth's atmosphere. Large meteoroids occasionally explode high above the surface, releasing enormous amounts of energy and producing pressure waves capable of being heard and felt across large distances. At this stage, however, investigators encountered a frustrating reality. The available evidence was incomplete. Thousands of witnesses had experienced the event. Instruments had recorded it. Yet no single explanation immediately accounted for every observation. This is the stage of an investigation that rarely appears in headlines, but often reveals the most about how science actually works. Contrary to popular belief, scientific discovery is not usually about finding answers quickly. It is about eliminating possibilities carefully. Meteorologists began reviewing atmospheric conditions. Seismologists examined waveform data. Aviation specialists checked flight activity. Astronomers searched for evidence of objects entering the atmosphere. Piece by piece, the puzzle slowly began taking shape. But before investigators could fully understand the first boom, something unexpected happened. Another explosion-like event would soon be reported hundreds of miles away. And suddenly what appeared to be a single unexplained occurrence started looking like part of a much larger pattern. The story could have ended there. One unexplained boom, one unusual afternoon, one investigation slowly working its way through the evidence. But 48 hours later, something happened that changed the entire narrative. Hundreds of miles farther north, another powerful explosion-like sound echoed across the sky. Once again, people reported rattling windows. Once again, homes vibrated. Once again, social media filled with the same question appearing in thousands of different forms. What was that? The timing alone was enough to attract attention. Unusual atmospheric events happen every year. Earth experiences meteor entries, sonic booms, thunderstorms, and a wide variety of natural phenomena. But when two highly visible events occur along the same coastline within such a short period of time, The human brain immediately begins looking for connections. We are pattern-seeking creatures. We instinctively want to know whether separate events are truly independent or whether they are pieces of a larger story. Scientists understand this tendency very well. In fact, one of the first rules of investigation is that coincidence should never automatically be mistaken for causation. Yet coincidence should not be ignored either. It should be examined. The second event occurred over one of the most densely populated regions of the northeastern United States. Witness reports arrived rapidly. Emergency dispatch centers received calls from concerned residents. Some people believed a nearby structure had exploded. Others suspected military aircraft. A few even wondered whether a small earthquake had occurred beneath the city. But, as investigators began collecting data, a very different picture emerged. Unlike the first boom, this event appeared to leave behind an additional clue. Somewhere over the Atlantic Ocean, instruments observing the atmosphere recorded something unusual. A brief flash, a transient burst of light, something bright enough to register on systems designed to watch Earth's atmosphere continuously. Suddenly, investigators had something they did not possess during the first event. They had a potential lead, and that lead would dramatically alter the speed at which explanations began to emerge. Yet before we follow that trail, it is worth pausing to appreciate just how unusual this situation had become. Two major atmospheric boom events. Two separate locations, less than 2 days apart, thousands of witnesses, national attention, and a growing collection of data pointing in different directions. Some evidence suggested a natural explanation. Other evidence suggested that at least one event might not fit neatly into the same category. The mystery was no longer about a single boom. The mystery was becoming a comparison between two booms. And sometimes comparisons reveal things that isolated events never can. Because when scientists investigate one unusual event, they ask what happened. When they investigate the similar events occurring close together, they begin asking why the evidence looks different. That difference would soon become the most important clue in the entire story. To understand why the second event received an explanation far more quickly than the first, we need to leave Earth entirely and travel 22,000 miles into space. High above the planet, positioned in geostationary orbit, a fleet of weather satellites watches the same regions of Earth continuously. These spacecraft are among the most sophisticated environmental monitoring systems humanity has ever built. They track hurricanes, thunderstorms, atmospheric rivers, wildfire smoke, and countless other phenomena. But one of their most remarkable abilities involves detecting sudden flashes of light years of light. Imagine staring at an entire hemisphere of Earth every second of every day. That is essentially what these satellites do. Specialized instruments continuously scan the atmosphere, searching for brief bursts of brightness. Most of the time, those flashes are produced by lightning. But occasionally, the instruments detect something else. A meteor entering Earth's atmosphere. A bright fireball. A bolide exploding high above the surface. When large meteoroids plunge into the atmosphere at tens of thousands of miles per hour, friction rapidly heats the object. The result can be an extraordinarily bright flash visible from enormous distances. From the perspective of a satellite, such an event often stands out clearly against the background of Earth below. This capability has transformed how scientists investigate atmospheric explosions. Decades ago, researchers depended largely on eyewitness reports. Today, satellites provide an independent record of what occurred, when it occurred, and where it occurred. For the second East Coast boom, investigators quickly noticed a possible atmospheric flash, approximately the right time and location. The significance of that observation cannot be overstated. Suddenly there was a mechanism capable of explaining both the light and the sound. The meteoroid enters the atmosphere. It fragments. It releases enormous energy. A bright flash appears. A pressure wave spreads outward. Minutes later, people hear and feel the boom. The sequence fits known physics remarkably well. Meteorologists reviewing the evidence rapidly converged on this possibility. Atmospheric scientists found it plausible. Astronomers began additional observations. The explanation was not yet confirmed, but for the first time investigators possessed a coherent theory supported by instrument data. Yet this development also created a new puzzle. Because if satellite observations could provide such a strong lead for the second boom, why had similar evidence not appeared for the first one? The absence of a flash was not merely a missing detail. It was becoming a critical piece of evidence in its own right. And as investigators would soon discover, sometimes what instruments fail to detect can be just as important as what they do detect. But hold that thought for a moment, because the most important clue in this entire investigation may not be the flash that was detected over the Atlantic. It may be the flash that was never detected over the first event at all. When scientists investigate unusual atmospheric phenomena, they are not simply looking for evidence that supports a hypothesis. They are equally interested in evidence that should exist but does not. In science, an absence can be as revealing as a presence. The first boom generated a remarkable amount of public attention. Thousands of people reported hearing it. Many felt it strongly enough to compare the experience to an explosion. Buildings vibrated, windows rattled. Pressure waves appeared to move across a broad region. Yet despite the size of the event, the usual signatures associated with a major meteor entry seemed strangely absent. There was no immediately obvious fireball report supported by multiple independent observations. No widely documented atmospheric flash. No rapidly emerging evidence trail pointing directly toward a large object entering Earth's atmosphere. That absence created a problem. If the first boom had been caused by the same mechanism as the second, investigators expected at least some similarities in the observational record. Instead, they found differences. And differences force scientists to ask uncomfortable questions. Were the two events actually unrelated? Was one caused by a meteor, while the other originated from an entirely different source? Or was there some factor affecting what observers and instruments were able to detect? These questions became increasingly important as agencies reviewed additional data. Meteor detection networks found no clear evidence of a large atmospheric entry corresponding to the first event. Satellite systems did not reveal the kind of obvious flash that had helped explain the second boom. The more investigators searched, the more the first event seemed to resist easy classification. This is where many public discussions begin moving in the wrong direction. Human beings dislike uncertainty. We prefer explanations, even weak ones, over unanswered questions. But scientific investigations work differently. A good investigator does not fill gaps with assumptions. A good investigator preserves the gaps until evidence arrives. And that is exactly what happened here. Instead of forcing an explanation, analysts allowed the uncertainty to remain. The result was unusual. One event rapidly moved toward a likely meteor interpretation. The other remained open. Not because nobody was looking, but because the available evidence did not support a confident conclusion. That distinction matters. An unanswered question is not proof of something extraordinary. It is simply an honest reflection of incomplete information. Yet the longer the first boom remained unexplained, the more attention it attracted, because people naturally began wondering what kind of event could generate such a powerful atmospheric shock without leaving behind the signatures investigators normally expect to see. And that question would soon direct attention toward another possible explanation, one involving some of the fastest objects ever built by human beings. To understand the next hypothesis, we first need to understand what a sonic boom actually is. Rather than counting sheep, most people think of a sonic boom as a sound. In reality, it is something much more dramatic. It is a shockwave. Whenever an aircraft travels through the atmosphere, it pushes air molecules aside. At ordinary speeds, those pressure disturbances move ahead of the aircraft and dissipate harmlessly. But when an object reaches the speed of sound, something remarkable happens. The pressure waves can no longer move away fast enough. They begin piling together, compressing into a single powerful shock front. When that shock front reaches an observer on the ground, it is heard as a sonic boom. The effect can be startling. Windows vibrate. Structures shake. People often describe it as an explosion because it arrives suddenly and with enormous force. Under the right atmospheric conditions, a sonic boom can travel surprisingly long distances. This immediately makes aircraft a natural suspect whenever unexplained booms occur. Modern military jets are capable of exceeding the speed of sound. Experimental aircraft can travel even faster. Hypersonic vehicles, now being actively developed and tested by several nations, move at speeds greater than Mach 5, more than 5 times the speed of sound. Such vehicles generate enormous shockwaves as they move through the atmosphere. The question, however, is not whether aircraft can create booms. The question is whether aircraft activity can explain the specific evidence associated with the first event. Investigators therefore began examining known flight operations. Were military aircraft present in the region? Were there reports of supersonic activity? Could a routine training mission account for what witnesses experienced? The answers were not immediately clear. Some possibilities appeared plausible. Others seemed less convincing. But what made this line of investigation so interesting was not merely the physics. It was the geography. The first boom occurred in a region surrounded by significant military infrastructure, training corridors, and heavily used airspace. Historically, sonic boom reports have occasionally emerged from similar areas. Most are eventually explained. A few remain unresolved. Yet before jumping to conclusions, scientists needed to answer another question. Even if an aircraft could produce the observed pressure wave, why did the event seem so widespread? Why did reports arrive from such large distances? The answer may have had less to do with the source itself and more to do with the atmosphere through which the shockwave traveled. Because, as investigators would soon discover, the sky above the east coast was behaving in a way that could dramatically amplify the reach of any powerful sound. But here is where the story takes an unexpected turn. What if the size of the boom was not telling us how powerful the source was? What if it was telling us something about the atmosphere itself? To most of us, air feels empty, invisible, passive, merely the medium through which weather happens. Yet the atmosphere is an extraordinarily complex structure made of layers, temperature gradients, pressure differences, and constantly shifting flows of energy. Under certain conditions, it can behave almost like a giant acoustic lens. It can bend sound, focus sound, and sometimes allow sound to travel far beyond the distances we would normally expect. This phenomenon has been known to scientists for decades. During major volcanic eruptions, explosions have occasionally been heard hundreds or even thousands of miles away. Certain meteor events have produced pressure waves detected across entire continents. The reason is not always the size of the source. Sometimes it is the condition of the atmosphere between the source and the observer. During the period when these East Coast booms occurred, meteorologists were monitoring a highly unusual atmospheric configuration across large portions of the eastern United States. The upper-level jet stream had developed a persistent wave pattern that slowed the movement of weather systems and created strong temperature contrasts between different layers of the atmosphere. To the average observer, these patterns appeared as unusual weather, fluctuating temperatures, and persistent regional instability. But to atmospheric scientists, they represented something else as well. They represented an environment capable of influencing how sound propagated through the air. When warm air sits above cooler air, a phenomenon known as a temperature inversion can develop. Under these conditions, sound waves that would normally disperse upward can become trapped. Instead of escaping into higher layers of the atmosphere, they bounce back downward and continue traveling horizontally. The result can be astonishing. Sounds become audible far beyond their normal range. Pressure waves remain coherent over much larger distances. Events that might normally affect a small region suddenly appear capable of shaking entire sections of a state. This matters because it changes how investigators interpret witness reports. If atmospheric conditions were enhancing sound propagation, then the enormous geographic footprint of the boom does not necessarily require an extraordinarily energetic source. A relatively modest atmospheric event could appear much larger simply because the atmosphere was helping carry its shockwave. In other words, the sky itself may have been amplifying the mystery. This realization forced investigators to become more cautious. The widespread reports could not automatically be used to estimate the size of the event. The atmosphere had become an active participant in the story. And once that possibility entered the analysis, something fascinating happened. Multiple competing explanations suddenly became plausible at the same time. A meteor could fit. A sonic boom could fit. Other atmospheric sources could potentially fit as well. The investigation was no longer narrowing. It was expanding. And that expansion would soon bring scientists face to face with one of the most frustrating realities in modern observation science. Sometimes the more data you collect, the more complicated the picture becomes. Most people imagine scientific investigations as a process that steadily reduces uncertainty. More observations led to more answers. More instruments led to more clarity. More data leads to greater confidence. Usually that is true, but not always. Sometimes additional information reveals contradictions that were previously invisible. And that is exactly what began happening as analysts continued examining the East Coast boom events. Every major observation network started contributing pieces of information. Seismic stations recorded unusual atmospheric signatures. Meteorologists reviewed satellite imagery. Aviation observers tracked known aircraft activity. Witnesses submitted thousands of independent reports describing what they saw, heard, and felt. Each new source of information added another layer to the investigation. Yet, instead of producing immediate agreement, the growing dataset exposed differences. Some observations appeared to support a meteor explanation. Others seemed more consistent with an atmospheric shockwave produced by human activity. Some reports aligned neatly with established physical models. Others remained difficult to explain. This is not unusual in complex investigations. The public often sees science as a collection of answers. Scientists see it as a process of resolving competing explanations. Every hypothesis must survive contact with the evidence. A theory that explains one observation but fails to explain 5 others becomes weaker. A theory that explains most observations gains strength. Over time, the balance shifts toward the explanation that best fits the complete picture. But during the early stages, uncertainty can actually increase. Imagine trying to assemble a puzzle while someone continues adding new pieces to the table. The image becomes richer, but it also becomes harder to interpret. That was the situation investigators found themselves facing. The second boom increasingly resembled a classic atmospheric meteor event. The first boom remained more difficult. Not impossible to explain, not necessarily extraordinary, simply harder to classify with confidence. And confidence matters enormously in science. Researchers are often willing to say, "We do not know yet," rather than support an explanation that lacks sufficient evidence. To the public, this can feel frustrating. To scientists, it is essential. The integrity of an investigation depends on preserving uncertainty until the evidence becomes strong enough to justify a conclusion. This is one reason why mysteries sometimes persist, even in an age of advanced technology. Instruments can record an event perfectly and still fail to reveal its source. Data can describe what happened without immediately explaining why it happened. The East Coast booms were becoming a textbook example of this principle. The monitoring infrastructure worked. The observations existed. The event was real. Yet the pathway from observation to explanation remained incomplete. And perhaps the most intriguing aspect of the entire story was not the explosions themselves. It was the realization that even in the 21st century, surrounded by satellites, sensors, algorithms, and vast networks of scientific instruments, The sky can still occasionally produce a question before it produces an answer. Let me ask you a question. If humanity can detect black holes billions of light years away, map distant galaxies, track asteroids across the solar system, and monitor hurricanes from space, how is it possible that a powerful atmospheric event occurring directly above one of the most densely monitored regions on Earth can remain uncertain even for few days? The answer reveals something important about the way observation actually works. We often imagine modern monitoring systems as all-seeing machines. In reality, every instrument is designed to observe only a specific part of reality. Weather satellites see some things exceptionally well and miss others entirely. Radar systems excel at detecting precipitation, but may overlook phenomena outside their design parameters. Seismic networks measure vibrations moving through the Earth but cannot directly identify every source responsible for those vibrations. Even the most sophisticated instruments are limited by the questions they were built to answer. Think of the scientific infrastructure surrounding Earth as a collection of specialized senses rather than a single unified intelligence. One system watches light, another watches motion, another watches pressure, another watches heat. When an unusual event occurs, scientists must combine all of these separate perspectives into a coherent picture. Most of the time, the process works remarkably well, but occasionally, reality produces an event that sits between categories. An event that leaves traces across multiple systems without fitting perfectly into any of them. The East Coast booms seem to occupy exactly that kind of territory. Consider what happened. Thousands of people heard the events. Instruments recorded pressure waves. Atmospheric scientists detected signatures consistent with known physical processes. Yet some pieces of evidence remained incomplete. Some observations pointed strongly in one direction. Others pointed somewhere else. The result was not confusion because the monitoring systems failed. The result was uncertainty because the systems were functioning exactly as designed. They were recording reality honestly, including the parts that remained unresolved. This distinction is critical. When the public hears that something remains unexplained, many assume that information is missing. Sometimes that is true, but often the reality is different. The information exists. The challenge lies in interpretation. Scientists may possess enormous amounts of data while still lacking enough evidence to confidently choose between competing explanations. In many ways, this is one of the most fascinating aspects of modern science. Knowledge does not eliminate mystery. Knowledge changes the shape of mystery. Every technological breakthrough allows us to observe more of reality, but it also reveals new layers of complexity hiding beneath the surface. The better we become at observing the world, the more we discover how much remains uncertain. And nowhere is that uncertainty more visible than in the sky above us, because every day millions of events occur within Earth's atmosphere. Most are understood immediately. A few are not. Those rare exceptions remind us that observation and understanding are not the same thing. We can witness an event long before we fully comprehend it. And that gap between seeing and understanding may be the most important clue in this entire story. Before satellites, before radar, before seismic monitoring networks and computer models, humanity relied on something much simpler. People looked up. It sounds almost primitive compared to modern technology, yet one of the most valuable scientific instruments in history remains the human observer. Every major atmospheric mystery begins with someone noticing that something unusual has happened. The East Coast booms were no exception. Long before experts began analyzing data, ordinary people experienced the events directly. They heard the sounds. They felt the pressure waves. They reported what they observed. In fact, one of the most remarkable aspects of modern science is that the public itself has become part of the detection network. Every smartphone owner is potentially a sensor. Every witness report contributes another piece of information. Every video recording, doorbell camera, and social media post adds context that may later prove valuable. Scientists understand this extremely well. That is why organizations around the world maintain public reporting systems specifically designed to collect eyewitness observations. Meteor events, earthquakes, atmospheric phenomena, and unusual sounds are often documented first by ordinary citizens. Individually, these reports may seem insignificant. Collectively, they can reveal patterns impossible to detect otherwise. Imagine a single witness hearing a loud boom. The report tells us very little. Now imagine thousands of witnesses reporting the same boom from different locations. Suddenly, investigators can estimate timing, direction, geographic extent, and even characteristics of the source. Human observations become data. The East Coast events generated exactly this type of response. Reports arrived from cities, suburbs, rural communities, and coastal regions. People described remarkably similar experiences despite being separated by large distances. This consistency immediately suggested that investigators were dealing with a genuine atmospheric event rather than isolated local disturbances. Yet human observations also introduce challenges. Memory is imperfect. Perception varies. Two people can experience the same event and describe it differently. One person hears an explosion. Another hears thunder. A third hears something that sounds like an aircraft. None of them are necessarily wrong. They are simply describing reality through the filter of human perception. This is why scientific investigations rarely rely on witnesses alone. Instead, eyewitness reports are compared against instrument data. When both sources point in the same direction, confidence increases. When they diverge, investigators look more carefully. The fascinating thing about the East Coast booms is that both forms of observation became essential. Without witnesses, the events might never have attracted widespread attention. Without instruments, the reports would remain anecdotes. Together, they created a detailed record of something unusual occurring in the atmosphere. And perhaps that is the deeper lesson hidden within this story. The modern scientific enterprise is not merely a collection of machines observing realities. It is a partnership between technology and human curiosity. Satellites watch the sky. Sensors monitor the Earth. But people are still the ones who notice when something feels strange. People are still the ones who ask questions. And sometimes, as in this case, a simple question asked by thousands of people at once becomes the beginning of an investigation that stretches from living rooms on the East Coast all the way east to satellites orbiting high above the planet. There is another question we need to answer before moving deeper into this mystery. Why does the sky sound like an explosion at all? Most people associate explosions with chemical reactions, military weapons, industrial accidents, or volcanic eruptions. Yet many of the loudest sounds humans have ever heard were not explosions in the traditional sense. They were shockwaves. The distinction matters because shockwaves can be generated in many different ways. A meteor entering the atmosphere at tens of thousands of miles per hour creates a shockwave. A fighter jet exceeding the speed of sound creates a shockwave. A rocket ray entering the atmosphere creates a shockwave. Even certain natural atmospheric processes can generate pressure disturbances that travel enormous distances. What all these phenomena share is speed. Specifically, they involve energy moving through the atmosphere faster than the atmosphere can smoothly accommodate it. Imagine a boat moving across a calm lake. At low speed, waves spread outward gently. Increase the speed enough, and the waves begin piling together into a larger wake. The atmosphere behaves similarly. When an object moves faster than sound itself, the pressure disturbances can no longer spread ahead of the object. Instead, they compress into a powerful wavefront. When that wavefront reaches the ground, people experience it as a sudden boom. The reason these events feel explosive is because the pressure change occurs almost instantly. Your ears detect it. Your windows detect it. Sometimes even the structure of your house detects it. The atmosphere briefly pushes against everything around you. This is why witnesses often describe sonic booms as explosions despite no explosion actually occurring. The sound is the result of atmospheric physics, not necessarily combustion. Understanding this helps explain why investigators were so cautious. The boom itself could not identify its own source. Multiple phenomena are capable of generating nearly identical acoustic signatures. A meteor exploding high above the Atlantic can produce a boom. A supersonic aircraft can produce a boom. Under some circumstances, other atmospheric events can produce remarkably similar effects. This means the sound alone was never going to solve a mystery. Scientists needed additional evidence. They needed flashes, trajectories, radar signatures, satellite detections, or other independent observations capable of narrowing the possibilities. The boom was merely the starting point. The real investigation began after the sound had already faded away. And as more evidence accumulated, something interesting started happening. The questions slowly shifted from what caused the boom to why do two apparently similar booms have such different evidence trails. That subtle shift would become one of the most important developments in the entire story. Humans are extraordinarily good at recognizing patterns. In fact, our ability to detect patterns helped our ancestors survive for hundreds of thousands of years. Recognizing seasonal changes, animal movements, weather shifts, and environmental dangers provided enormous evolutionary advantages. But this same strength can sometimes become a weakness. We often see patterns even when none exist. The moment the second East Coast boom occurred, countless people began connecting it to the first. The timing seemed suspicious. The locations seemed related. The similarities seemed obvious. Social media rapidly filled with theories attempting to explain both events through a single cause. Some explanations were plausible. Others were wildly speculative. Yet from a scientific perspective, there was a fundamental problem. Similar events do not necessarily share the same source. Consider thunderstorms. Two storms occurring within days of each other may have completely different origins. The same is true for earthquakes, meteor entries, and atmospheric disturbances. Similar outcomes do not automatically imply a common cause. This principle sits at the heart of scientific investigation. Correlation is not causation. The fact that two unusual events happened within 48 hours does not prove they were connected. At the same time, scientists cannot simply dismiss the coincidence. Patterns deserve investigation. They just do not deserve automatic conclusions. This balancing act is one of the hardest parts of scientific reasoning. Investigators must remain open to potential connections while simultaneously resisting the temptation to assume those connections exist. In the case of the East Coast booms, this challenge became increasingly apparent. One event appeared to be moving toward a meteor explanation. The other remained more ambiguous. The evidence profiles looked different. The observational records looked different. Yet public attention increasingly treated them as part of a single narrative. This created a fascinating contrast between scientific thinking and human intuition. Intuition seeks stories. Science, evidence. Intuition wants closure. Science tolerates uncertainty. Intuition asks whether two events feel related. Science asks whether the data supports that relationship. Neither approach is inherently wrong. Both of them counting sheep. Both emerge from deeply human ways of understanding the world. But when investigating atmospheric mysteries, evidence must ultimately take priority. Otherwise, every coincidence becomes a conspiracy and every unanswered question becomes an extraordinary claim. The East Coast booms remind us how difficult this balance can be. The events occurred close together. They attracted enormous public attention. They generated thousands of reports. And yet the most honest answer remained surprisingly simple. Scientists were still gathering information. Some questions had strong provisional answers. Others did not. The mystery was not that investigators lacked curiosity. The mystery was that reality itself was still revealing its details one piece at a time. And sometimes the hardest thing for both scientists and the public to accept is that nature does not operate according to our desire for immediate explanations. Sometimes the evidence arrives slowly. Sometimes the picture remains incomplete. And sometimes the most scientifically accurate answer is simply that we are still learning what happened. At this point in the story, it is tempting to imagine satellites as giant cameras floating in space, recording everything that happens below with perfect clarity. But the reality is far more interesting. Satellites do not see the world the way humans do. They do not simply look down and watch events unfold like observers standing on a balcony. Instead, they measure specific forms of energy. Some detect visible light. Others monitor infrared radiation. Others measure water vapor, cloud structure, atmospheric temperature, or lightning activity. Each satellite sees only part of reality. When scientists say a satellite detected something unusual, what they really mean is that one of its instruments measured a signal that differed from the background environment. This distinction becomes extremely important when discussing the East Coast booms. The event that appeared increasingly consistent with a meteor was not identified because someone literally watched a space rock explode from orbit. Instead, specialized instruments detected a brief atmospheric signature that matched patterns previously associated with bright meteors known as bolide death. These instruments continuously scan vast portions of Earth, searching for sudden flashes that stand out against the normal brightness of the atmosphere. Most flashes come from lightning. Occasionally, they come from something else. The challenge is determining exactly what that something else might be. Imagine trying to identify a single camera flash occurring somewhere across an entire continent, while simultaneously monitoring oceans, clouds, cities, and storms. That is essentially the task these systems perform every day. Most of the time they succeed remarkably well, yet they are not perfect. A detection is not automatically an explanation. It is a clue. Scientists must still compare it against weather conditions, witness reports, timing data, and other observations. This process is why the second boom began moving toward a likely explanation relatively quickly. The satellite evidence provided a starting point. Investigators suddenly had something measurable that aligned with a known physical mechanism. But the first boom remained different. There was no equally compelling atmospheric flash drawing immediate attention. No obvious signature pointing toward a large meteor entry. No single piece of evidence that dramatically simplified the investigation. This difference illustrates an important lesson about modern science. The speed of an explanation often depends less on the event itself and more on the quality of the available evidence. Two similar events can produce very different investigative outcomes if one leaves behind a stronger observational record than the other. The mystery was therefore no longer just about atmospheric explosions. It was becoming a lesson in how scientific knowledge is assembled. One clue at a time. One observation at a time. One piece of evidence at a time. And sometimes, the difference between a solved mystery and an unsolved one is nothing more than a single signal captured by a sensor orbiting thousands of miles above the Earth. There is another layer to this story that most people never think about. Above the cities, forests, mountains, and coastlines of the United States exists an invisible transportation network unlike anything on the ground. Thousands of aircraft move through this aerial system every day. Commercial airliners cross the continent. Military aircraft train in designated corridors. Research vehicles conduct experiments. Weather balloons rise into the atmosphere. Satellites pass overhead. Rockets occasionally climb through the upper sky. From the perspective of someone standing on the ground, the sky often appears empty. In reality, it is one of the busiest environments on Earth. This matters because every atmospheric mystery must eventually confront a simple question. Could human activity have produced what people experience? The question is not unreasonable. Human beings routinely generate enormous amounts of energy in the atmosphere. Modern fighter aircraft can travel faster than sound. Advanced military platforms can move even faster. Rocket launches release tremendous energy. Experimental aerospace programs continue pushing the boundaries of speed and altitude. The atmosphere above North America is not merely a natural environment. It is also an active technological environment. This is why investigators always examine airspace activity when unusual booms occur. They look for known aircraft. They review flight operations. They compare timing information. They analyze whether observed pressure waves match known aerodynamic phenomena, rather than counting sheep. Most of the time, these efforts quickly identify a source. Sometimes they do not, and that distinction is critical. The absence of an immediate explanation does not automatically imply secrecy, mystery, or extraordinary causes. It often reflects something much simpler. The atmosphere is an incredibly complicated place. Signals overlap. Events occur simultaneously. Observations arrive from multiple systems with different levels of precision. Building a complete picture takes time. Nevertheless, the possibility of aircraft remained part of the discussion surrounding the first boom, not because investigators had proven such a connection, but because sonic booms remain one of the most physically plausible explanations for loud atmospheric shockwaves. The challenge was finding evidence strong enough to support or reject that possibility. This is where the investigation became increasingly interesting, because the more analysts examined the event, the more they realized that the atmosphere itself might be complicating the picture. A sound produced in one location could potentially be heard far away here. A shockwave could travel differently depending on atmospheric conditions. Witnesses might accurately report what they experienced while still misjudging where the source originated. Suddenly, even basic assumptions became uncertain. And when assumptions become uncertain, investigations become much more difficult. Yet they also become much more revealing, because every layer of complexity exposes another hidden truth about the world we live in. The East Coast booms were no longer simply unexplained sounds. They were becoming a window into the extraordinary complexity of the atmosphere itself and the immense challenge of understanding everything that happens within. If the East Coast explosions seem unusual, it is because they are, but they are not, entirely unprecedented. Long before satellites, radar systems, seismic networks, and modern communication technology existed, people were already reporting unexplained booms coming from the sky. Historical records contain hundreds of accounts describing sudden explosive sounds with no visible source. Coastal communities heard them. Mountain towns heard them. Sailors at sea heard them. Entire generations occasionally experienced atmospheric noises that seemed to arrive from nowhere and disappear just as quickly. One of the most famous examples comes from the eastern coastline of North America itself. For centuries, residents along portions of the Atlantic coast reported hearing what became known as skyquakes or mystery booms. Witnesses described sounds resembling distant artillery fire, underground explosions, or cannon blasts echoing across the horizon. Sometimes the events occurred during clear weather. Sometimes they appeared without any accompanying visual phenomenon at all. These reports became so common that entire local traditions developed around them. Scientists have proposed many explanations over the years. Distant thunder, carried by unusual atmospheric conditions. Small earthquakes, offshore storms, meteors, military activity, atmospheric pressure disturbances. The reality is that multiple explanations may account for different events. There is no single cause behind every mysterious boom ever reported. What makes these historical accounts fascinating is that they reveal something important about human perception. We often assume unusual events are unique to our era because we encounter them through modern media. In reality, many atmospheric mysteries have accompanied humanity for centuries. The difference is that today we possess vastly more tools for investigating them. Yet even with all our technology, some uncertainty remains. That fact should not discourage us. In many ways, it should inspire us, because it reminds us that nature still contains surprises. The atmosphere remains a dynamic and complex system. The sky above us continues producing phenomena that challenge our understanding. The East Coast booms belong to a long historical tradition of events that captured public attention precisely because they sat at the boundary between observation and explanation. People heard something real. Instruments recorded something real. The challenge was connecting those observations to a specific cause. And that challenge has accompanied atmospheric science for generations. The difference now is that every new event leaves behind far more evidence than ever before. Every witness report, every satellite observation, every seismic measurement becomes part of a growing archive of knowledge. The mystery may not disappear immediately, but each investigation teaches us something new about how the atmosphere behaves. And sometimes the most valuable discoveries emerge not from the answers we find, but from the questions we are forced to ask. There is a surprising fact that rarely enters public discussion. Earth is constantly being bombarded from space. At this very moment, tiny particles from comets, asteroids, and ancient collisions throughout the solar system are entering the atmosphere. Most are no larger than grains of sand. They burn up harmlessly high above the surface, creating faint streaks of light that most people never notice. Every night, millions of these microscopic visitors arrive. Occasionally, however, something larger appears. A pebble-sized object can create a bright meteor. A rock the size of a baseball can generate an impressive fireball. Larger objects can produce atmospheric explosions powerful enough to be detected across entire regions. The reason most people are unaware of this constant bombardment is simple. Earth's atmosphere is extraordinarily effective at protecting us. It acts like a gigantic shield surrounding the planet. Objects traveling at cosmic speeds encounter air resistance so intense that they rapidly heat, fragment, and often vaporize completely before reaching the ground. This process occurs so routinely that we rarely think about it. Yet every bright meteor represents an extraordinary transfer of energy. Consider an object entering the atmosphere at 40,000 miles per hour. Even a relatively small mass can carry enormous kinetic energy. When that energy is released during atmospheric fragmentation, the resulting flash can rival the brightness of the sun. The accompanying shockwave can travel across vast distances. Windows may rattle. Buildings may shake. People may hear what sounds like an explosion. This is one reason meteor explanations are taken so seriously whenever large atmospheric booms occur. The physics is well understood. The mechanism is real. Similar events have been documented many times throughout history. Yet what makes the East Coast case so interesting is not merely the possibility of a meteor. It is the contrast between the two events. One appeared to leave behind evidence consistent with a known atmospheric entry. The other did not. That distinction remains the central puzzle, because if both booms had produced identical evidence, the story would be much simpler. Investigators would likely reach similar conclusions for both. Instead, the evidence diverged. One pathway became increasingly clear, the other remained uncertain. This divergence forces us to confront an uncomfortable reality about scientific investigation. Nature does not always provide equal amounts of evidence. Some events leave behind abundant clues. Others leave behind only fragments. Some mysteries solve themselves quickly. Others resist explanation. The atmosphere is not obligated to produce neat case studies for human investigators. It simply behaves according to physical laws, leaving us to reconstruct what happened afterward. And when we attempt that reconstruction, we often discover that the sky is far more active, far more dynamic, and far more complicated than we ever imagined while looking up from the ground below. There is a point in every scientific investigation when the focus shifts. The original question begins to dissolve, replaced by a more important one. For the East Coast boom, that moment arrived when investigators stopped asking what people heard and started asking why the evidence looked so different between the two events. Up until this point, most public attention had been directed toward the sounds themselves. The explosions were dramatic. The witness reports were compelling. The videos and social media discussions created a sense of urgency. But scientists were becoming increasingly interested in something less visible. They were interested in the asymmetry. Why did one event produce what appeared to be a coherent chain of evidence, while the other remained stubbornly incomplete? This question matters because science advances through comparison. A single observation can be misleading. Two observations allow contrast. Contrast reveals structure. Structure reveals mechanisms. The second event appeared to have a potential atmospheric flash. Witness reports consistent with a high-altitude source, and a plausible physical explanation involving a meteoroid entering Earth's atmosphere. The first event lacked several of those elements. It produced a large acoustic footprint. It generated thousands of reports. Yet some of the expected supporting evidence remained absent. The difference did not necessarily imply different causes, but it demanded further investigation. Imagine two footprints in fresh snow. One is clear and sharply defined. The other is partially obscured. Both may have been created by the same person, yet the available evidence looks very different. Investigators face a similar challenge. They cannot simply assume identical origins because the events appear similar on the surface. They must work with the evidence that actually exists. This is one of the most difficult concepts for the public to appreciate. Scientific conclusions are not based on what feels likely. They are based on what can be supported by observation. Sometimes that means accepting uncertainty longer than we would prefer. The East Coast booms became a perfect example of this principle. The investigation was no longer about finding the fastest explanation. It was about finding the most defensible explanation. And that distinction would ultimately determine how scientists interpreted everything that followed. Because the deeper investigators looked, the clearer it became that the most important part of the story was not the booms themselves. It was the evidence they left behind. One reason the East Coast events attracted so much attention is that most people assume atmospheric explosions are extremely rare. In reality, they are more common than many realize. Every year, Earth's atmosphere absorbs the energy of countless incoming objects. Most are tiny. Most go completely unnoticed. But occasional larger events occur. The vast majority happen over oceans, deserts, forests, or sparsely populated regions where few people are present to witness them. This creates a powerful illusion. We tend to believe unusual atmospheric events are rare because we only hear about the ones that occur near people. In statistical terms, our perception is shaped by observational bias. Imagine a bright meteor exploding above the middle of the Pacific Ocean. Millions of square miles of ocean lie beneath it. No cities, no highways, no social media posts, no doorbell cameras. The event may be physically impressive, yet almost nobody notices. Now imagine a similar event occurring above a major metropolitan region. Suddenly thousands of witnesses report it. Cameras record it. News organizations investigate it. The event becomes a national story. The physical phenomenon may be similar, but the public response is dramatically different. Scientists account for this bias whenever they study atmospheric events. They understand that detection depends not only on the event itself, but also on where and when it occurs. This is one reason modern monitoring systems are so valuable. Instruments do not care whether an event occurs above a city or an ocean. They record what they can detect. Over time, these observations have revealed a fascinating reality. Earth's atmosphere experiences far more energetic events than most people realize. Small atmospheric explosions occur regularly. Bright fireballs are observed every year. Sonic booms from natural and human-made sources happen far more often than newspaper headlines might suggest. What makes the East Coast booms unusual is not necessarily their existence. It is the combination of factors surrounding them: their timing, their locations, their visibility, their extensive witness reports, and most importantly, the contrasting evidence trails they produced. This distinction is critical. An event does not need to be unprecedented to be scientifically interesting. In fact, some of the most valuable investigations involve phenomena that are already known but not fully understood. Each new occurrence provides another opportunity to compare observations, test explanations, and refine models. That is exactly what investigators were doing here. They were not merely trying to solve a mystery. They were using the mystery to learn more about how the atmosphere behaves. And in many ways, that is the essence of science itself. Every unexplained event becomes an experiment that nature conducts on our behalf. The question is whether we are capable of interpreting the results correctly. And as we are about to discover, that challenge becomes even greater when we consider the vast number of things happening above our heads that we never notice at all. At any given moment, thousands of events are unfolding above Earth that never enter public awareness. Tiny meteors burn up in the upper atmosphere. Electrical discharges flash inside distant storm systems. High-altitude winds reshape entire weather patterns. Aircraft cross invisible corridors stretching from one continent to another. Satellites glide silently overhead at thousands of miles per hour. Yet most of us notice none of it. Human perception evolved to focus on what directly affects survival. We pay attention when something becomes loud, bright, dangerous, or unusual. Everything else fades into the background. The East Coast booms crossed that threshold. They became impossible to ignore. The sounds were powerful enough to demand attention. The mystery was compelling enough to hold it. But the truth is that the atmosphere is constantly producing events that would seem extraordinary if we happened to observe them closely. Consider lightning. At any given second, dozens of lightning strikes are occurring somewhere on Earth. Over the course of a day, millions of electrical discharges release enormous amounts of energy into the atmosphere. Most people experience only a tiny fraction of this activity. The same principle applies to meteors. Scientists estimate that tens of tons of extraterrestrial material enter Earth's atmosphere every single day. Most of it arrives unnoticed. Most burns up harmlessly. Yet if even a small percentage of those events occurred above major cities, public perception of the sky would be dramatically different. We would see the atmosphere not as a quiet space above us, but as a constantly changing environment filled with motion, energy, and interactions. This perspective matters because it changes how we interpret unusual events. The East Coast booms did not occur in isolation from the rest of nature. They occurred within an atmosphere that is perpetually active. An atmosphere that transports heat around the planet, channels powerful winds, absorbs incoming objects from space, and occasionally produces phenomena that surprise even experienced observers. One reason atmospheric mysteries capture our imagination so effectively is that they reveal this hidden activity. They pull back the curtain for a moment and remind us that the sky is not empty. It is dynamic, alive with processes operating on scales both enormous and microscopic. The boom that startled thousands of people was only one visible ripple in a vast ocean of atmospheric activity. And perhaps that is why these events resonate so strongly. They momentarily force us to notice the environment we usually take for granted. They remind us that we live beneath a complex system that is continuously changing, continuously interacting with the wider universe, and continuously producing events that most of us never see. The East Coast booms may eventually receive complete explanations, or some aspects may remain uncertain. Either way, they have already accomplished something valuable. They have reminded us to look up. The strange irony of this story is that it unfolded during one of the most monitored periods in human history. Never before have we possessed so many tools for observing our planet. Satellites watch weather systems continuously. Seismic networks monitor Earth's crust around the clock. Radar installations scan the atmosphere. Astronomical observatories search for incoming objects from deep space. Millions of cameras record daily life across cities and towns. Smartphones instantly connect eyewitnesses across entire continents. If a similar atmospheric event had occurred 200 years ago, it might have become little more than a local legend. People would have heard the boom. Stories would have spread. Explanations would have varied wildly. Eventually, the event would fade into memory. Today, something very different happens. Every unusual occurrence generates data. Instruments record it. Observers discuss it. Scientists analyze it. The event enters the permanent historical record. In many ways, this transformation represents one of the greatest achievements of modern civilization. Humanity has built an observational network that spans the globe and extends into space itself. Yet the East Coast booms reveal an important limitation. Observation is not the same as understanding. Collecting information is only the first step. Interpretation remains essential. Imagine standing in a library containing every book ever written in human history. Possessing the books does not automatically grant knowledge. The information must still be organized, analyzed, and understood. Scientific data works the same way. A sensor may record an event perfectly. That does not guarantee an immediate explanation. The East Coast booms illustrate this principle beautifully. The monitoring systems functioned. Witnesses reported what they experienced. Instruments captured relevant information. Scientists began analyzing the evidence. Yet uncertainty persisted. Not because the system failed, but because reality is often more complicated than our initial assumptions. This should not be viewed as a weakness. It is actually one of the strengths of the scientific process. Science does not demand certainty where certainty does not yet exist. It allows unanswered questions to remain open until sufficient evidence becomes available. In an age of instant information, this can feel uncomfortable. We are accustomed to rapid answers, immediate conclusions, quick explanations. Nature does not always cooperate. Sometimes it reveals its secrets gradually. Sometimes the most honest answer remains we are still investigating. The East Coast booms became a powerful reminder of that reality. They showed that even with extraordinary technology, there are moments when observation outruns interpretation. Moments when we know something happened before we fully understand why it happened. Those moments are not failures of science. They are opportunities for science. Because every unanswered question becomes an invitation to learn something new. And as we continue following this story, we are about to encounter perhaps the most important question of all. Not what caused the booms, not why they were heard, but what these events reveal about the relationship between uncertainty and knowledge in the modern age. There is a tendency in modern culture to view uncertainty as a weakness. We celebrate certainty. We reward confidence. We often assume that the fastest answer is the best answer. Yet throughout the history of science, some of the greatest discoveries emerged precisely because someone was willing to admit they did not yet know. The East Coast booms offer a perfect example. Imagine two different responses to an unexplained atmospheric event. In the first scenario, investigators immediately choose an explanation, whether or not the evidence fully supports it. The mystery disappears quickly, but the opportunity to learn disappears with it. In the second scenario, investigators carefully examine the evidence, acknowledge what remains unknown, and allow the question to remain open until stronger conclusions become possible. This second approach is slower. It can feel unsatisfying, yet it is the foundation of reliable science. The remarkable thing about the East Coast events is not that uncertainty existed. The remarkable thing is that uncertainty was preserved. Scientists resisted the temptation to fill every gap immediately. They followed the evidence where it led. In one case, the evidence increasingly pointed toward a plausible explanation involving an atmospheric meteor event. In the other, the evidence remained less definitive. Rather than forcing a conclusion, investigators allowed the ambiguity to remain visible. This may seem like a small detail, but it reflects something profound about the scientific method. Science is not a machine that produces certainty. It is a process that gradually reduces uncertainty, sometimes rapidly, sometimes slowly, sometimes incompletely. The public often sees only the final answer. Scientists spend most of their time navigating the space before the answer arrives. The East Coast booms existed within that space, a place where observations were real, data was accumulating, and conclusions were still evolving. This process can be frustrating because humans naturally crave closure. We want the story to end neatly. We want a final explanation that resolves every loose thread. Nature does not always provide that kind of ending. Sometimes evidence remains incomplete. Sometimes competing explanations survive longer than expected. Sometimes the most accurate description of reality includes uncertainty itself. Far from being a flaw, this honesty is one of science's greatest strengths. It allows investigators to separate confidence from speculation. It prevents temporary assumptions from becoming permanent misconceptions. And it ensures that future evidence can continue improving our understanding. The East Coast booms remind us that uncertainty is not the opposite of knowledge. It is often the pathway to knowledge. Every unanswered question points toward an area where learning remains possible. Every mystery reveals a boundary between what we understand and what we are still discovering. And perhaps that boundary is one of the most fascinating places in all of science. For most of human history, atmospheric events were local experiences. A strange light appeared above a village. A loud sound echoed across a valley. A meteor flashed across the horizon. Only the people nearby witnessed it. Their accounts remained isolated. Their interpretations varied. The event belonged to a specific place and time. Today, something very different happens. The moment an unusual event occurs, information begins spreading across an interconnected planetary network. Witnesses upload videos. Sensors record measurements. Scientists exchange observations. Journalists investigate. Amateur researchers contribute analyses. Within minutes, a local event can become a global conversation. The East Coast booms demonstrated this transformation perfectly. Thousands of people experienced the events directly. Millions learned about them indirectly. Within hours, discussions were taking place across the country and beyond. Atmospheric scientists examined the data. Meteor enthusiasts searched for evidence of fireballs. Aviation observers reviewed flight activity. Ordinary citizens contributed observations from their homes. This interconnected response reveals something remarkable about modern civilization. Humanity has effectively become a distributed observation network. The distinction between professional observer and public observer is increasingly blurred. Satellites monitor the sky from orbit. Scientists operate specialized instruments. But millions of ordinary people now participate in the process of observation as well. Every smartphone camera becomes a potential scientific tool. Every eyewitness report becomes a possible data point. Every unusual event generates a collective effort to understand what happened. This development has dramatically increased our ability to investigate rare phenomena. Events that might once have passed unnoticed now leave behind extensive records. Yet it has also created new challenges. Information travels faster than verification. Speculation spreads faster than evidence. The desire for explanations often outpaces the availability of reliable data. This is why scientific discipline becomes so important. Investigators must separate observations from assumptions, facts from interpretations, evidence from speculation. The East Coast booms became a fascinating case study in this process. Public curiosity was enormous. Information flowed rapidly. Yet the most reliable conclusions emerged from careful analysis rather than immediate reaction. This balance between curiosity and caution lies at the heart of modern science. Curiosity motivates investigation. Caution protects accuracy. Together they allow us to explore mysteries without losing sight of reality. And perhaps that is one of the most encouraging lessons hidden within this story. The world remains full of unanswered questions. Yet humanity has never been better equipped to investigate them. Every year our instruments improve. Every year our understanding deepens. Every year we become more capable of transforming mysteries into knowledge. The East Coast booms may represent only a small chapter in that ongoing story. but they remind us that the story itself is still being written. As strange as these booms may seem from the ground, they become even more fascinating when viewed from a cosmic perspective. We often think of Earth as a separate world, isolated from the rest of the universe. But that is an illusion created by everyday life. In reality, our planet exists within a dynamic cosmic environment. Every second, Earth moves through space at roughly 67,000 miles per hour. As it orbits the Sun, the solar system itself travels around the center of the Milky Way at more than 500,000 miles per hour. Meanwhile, countless particles, fragments, and remnants from the formation of the solar system continue crossing our planet's path. The atmosphere serves as our protective boundary against this constant cosmic traffic. Most of the time, that protection operates invisibly. Tiny particles burn up without notice. Small meteors flash briefly overhead before disappearing forever. Yet every so often, the universe reminds us that Earth is not isolated. Something arrives from space carrying enough energy to announce its presence. When that happens, the event can feel profoundly local. A loud boom, a shaking window, a startled neighborhood. But the origin may lie millions or even billions of miles away. A small rock exploding in Earth's atmosphere could have spent millions of years orbiting the Sun before encountering our planet. Some meteoroids are fragments of ancient asteroids that formed during the earliest history of the solar system. Others may originate from long-period comets, whose journeys began far beyond the orbit of Pluto. This means that a sound heard by a family sitting in their living room could ultimately trace its origins back to events occurring before complex life existed. On Earth, that realization changes the scale of the story. The East Coast booms are not merely atmospheric events. They are reminders that Earth remains connected to the wider universe. The boundary between space and atmosphere is not a wall. It is a region of constant interaction. Every meteor, every fireball, every atmospheric entry represents a moment when cosmic history briefly intersects with human history. Even if the first boom ultimately proves unrelated to a meteor, the broader lesson remains. Earth is not separate from the cosmos. We are immersed within it. The sky above us is not simply weather and cloud. It is also the point where our planet continuously interacts with the larger universe beyond. And sometimes those interactions arrive with enough force to shake the ground beneath our feet. Imagine for a moment that the East Coast booms occurred in the year 1926 instead of 2026. The sounds would still have been heard. The windows would still have rattled. People would still have been startled. But almost everything else would be different. There would be no social media, no satellite observation, no nationwide seismic monitoring networks, no instant communication connecting thousands of witnesses. Residents in one town might believe an explosion had occurred nearby. People in another town might assume thunder was responsible. Newspapers would collect local accounts. Rumors would spread. Explanations would vary from community to community. Most likely, the event would gradually pass into local folklore. Historians might later discover scattered reports describing a mysterious boom heard across portions of the East Coast. But the event itself would remain largely unresolved. This thought experiment reveals something important. Modern technology does not eliminate mystery. What it changes is our ability to investigate mystery. The East Coast booms generated an extraordinary amount of evidence compared to similar events in the past. Scientists compare satellite observations, witness reports, atmospheric data, seismic measurements, and aviation records. Even when uncertainty remained, investigators possessed far more information than any previous generation could have imagined. This perspective highlights how dramatically humanity's relationship with the unknown has changed. Throughout most of history, unexplained phenomena often remained unexplained forever. Today, even when answers are incomplete, investigations continue. New data can emerge. Archived observations can be revisited. Improved models can be applied years later. The story does not necessarily end when public attention fades. In some cases, the most important discoveries occur long after an event takes place. This is one reason scientists preserve observational records so carefully. Today's unanswered question may become tomorrow's solved problem. A future researcher examining archived data might notice a detail that current investigators overlooked. A new instrument might reveal information unavailable today. A broader pattern might emerge as additional events occur. Knowledge evolves. Understanding deepens. The East Coast booms exist within this larger process. They are not merely isolated events. They are entries in a growing historical record documenting how the atmosphere behaves and how humanity observes it. 100 years ago, the story might have ended with confusion. Today, it continues through investigation. And perhaps 100 years from now, future generations will look back at events like these and wonder how we ever found them mysterious at all. That possibility is one of the most beautiful aspects of science. Every mystery contains the seeds of future understanding. Every unanswered question represents knowledge waiting to be discovered. And every unusual sound from the sky reminds us that the process of discovery is far from complete. By now, you may have noticed something unusual about the story. We have spent hours examining atmospheric physics, satellite observations, meteors, sonic booms, aircraft, witness reports, and scientific investigations. Yet despite all of that information, one uncomfortable reality remains. Some questions are still open. And perhaps the most important lesson hidden within the East Coast booms is learning how to live with that fact. Modern society often creates the expectation that every question should have an immediate answer. Search engines provide results in seconds. Artificial intelligence responds instantly. News spreads across the world in minutes. We have become accustomed to speed. But nature does not operate according to our schedule. The atmosphere does not reveal its secrets simply because we demand them. Sometimes evidence arrives slowly. Sometimes data remains incomplete. Sometimes reality refuses to fit neatly into our categories. This can feel frustrating. Yet from a scientific perspective, it is perfectly normal. In fact, uncertainty is often a sign that investigators are being careful. Consider the alternative. Imagine if every unusual event immediately received a definitive explanation regardless of the evidence. Investigations would be faster, but accuracy would suffer. Assumptions would replace observations. Confidence would replace caution. The East Coast booms remind us why scientific restraint matters. When the evidence strongly supported a particular interpretation, scientists moved toward that interpretation. When the evidence remained incomplete, uncertainty remained visible. This distinction is not weakness. It is intellectual honesty. One of the most remarkable features of science is its willingness to say, "We do not know yet." Few human institutions are comfortable with those words. Yet scientific progress depends on them. Every major discovery begins with an acknowledgement of uncertainty. We do not know what causes this. We do not know how this works. We do not know what happened here. Those admissions create space for investigation. They create opportunities for learning. The East Coast booms occupy exactly that space. They remind us that the boundary between knowledge and mystery is not a failure of understanding. It is the frontier of understanding. Every unanswered question marks the edge of what humanity currently knows. Beyond that edge lies future discovery. And perhaps that is more exciting than any immediate explanation could ever be here. When most people think about Earth, they imagine a stable world beneath their feet. Mountains, oceans, cities, landscapes that appear permanent on human timescales. Yet the reality is very different. Earth is a dynamic planet. The atmosphere moves continuously. Oceans circulate enormous quantities of heat. Tectonic plates shift slowly beneath the surface. Magnetic fields fluctuate. Weather systems reorganize themselves every day. Even the space surrounding our planet is filled with activity. We often describe Earth as a planet, but in many ways it behaves more like a living system, not alive in the biological sense, but alive with movement, interaction, and change. The East Coast booms offer a reminder of this reality. They emerged from a planet that is never truly still. Pressure waves travel through the atmosphere. Energy moves between different layers of air. Objects enter from space. Aircraft cross invisible pathways overhead. Natural and human systems interact continuously. Most of this activity occurs beyond our awareness. Then suddenly, an event becomes impossible to ignore. A boom echoes across a region. A bright flash appears overhead. Windows shake. People stop what they are doing and look up. For a brief moment, the hidden activity of the atmosphere becomes visible, or in this case audible. These moments are valuable because they reconnect us with the reality of the world we inhabit. We spend much of our lives indoors, surrounded by technology, disconnected from the natural systems operating around us. Atmospheric mysteries pull our attention back toward those systems. They remind us that we live beneath a vast, active sky. A sky filled with processes that have been operating long before human civilization emerged and will continue long after we are gone. The East Coast booms may eventually receive complete explanations, or they may remain partially unresolved. But regardless of the final outcome, they have already served an important purpose. They have encouraged millions of people to pay attention, to ask questions, to think about the atmosphere not as empty space, but as a complex environment worthy of curiosity and investigation. In a world increasingly dominated by screens and distractions, that renewed sense of wonder may be one of the most valuable outcomes of all. Because every scientific journey begins in the same way, not with certainty, not with answers, but with curiosity strong enough to make us stop, look up, and ask what just happened. At the beginning of this journey, the mystery seemed straightforward. A loud explosion-like sound echoed across parts of the East Coast. Thousands of people heard it. Many felt it. Investigators began searching for answers. On the surface, the story appeared to be about identifying a source. Was it a meteor? A sonic boom? An atmospheric anomaly? A human-made event? Yet after following the evidence through satellites, atmospheric science, seismic monitoring, witness reports, and historical comparisons, something interesting emerges. The boom itself may not be the most important mystery after all. The real mystery is how little most of us think about the sky until it demands our attention. Every day we move beneath an atmosphere nearly 60 miles deep. We trust it. We depend on it. It regulates temperature, protects us from harmful radiation, absorbs incoming objects from space, and makes life possible. Yet most of its activity occurs beyond our awareness. We notice weather when it disrupts plans. We notice storms when they become dangerous. We notice atmospheric events when they become loud enough to interrupt ordinary life. The East Coast booms did exactly that. They interrupted normality. For a few brief moments, thousands of people were reminded that the atmosphere is not a static backdrop. It is an active system filled with energy, motion, and interactions occurring continuously above our heads. In many ways, the event functioned like a spotlight. It illuminated processes that are normally invisible. It forced people to think about pressure waves, atmospheric propagation meteors, and monitoring systems that they might never otherwise consider. This is one reason scientific mysteries are so valuable. They disrupt assumptions. They challenge the illusion that we already understand everything important. They remind us that reality is often more complicated than it appears. The East Coast booms may eventually receive complete explanations. They may not. But either outcome is less important than the perspective they provide. Because the true lesson of this story is not that something unusual happened. Unusual things happen all the time. The true lesson is that a single unexplained event can reveal an entire hidden world operating around us every day. A world of atmospheric dynamics, cosmic interactions, technological observation systems, and scientific investigation. A world that continues functioning whether we notice it or not. The boom captured attention. The atmosphere is what deserves it. And perhaps that is why stories like this continue to fascinate us. They remind us that mystery is not something that exists only in distant galaxies or deep oceans. Sometimes it exists directly above our heads, hidden within the sky we think we know so well. Imagine a scientist 50 years from now studying atmospheric events from the early 21st century. They may have access to technologies we cannot yet imagine, monitoring systems far more sensitive than today's instruments. Artificial intelligence capable of reconstructing events with extraordinary precision. Global observation networks covering every corner of the atmosphere in real time. To them, the East Coast booms may appear very different than they do to us today. Events that seem uncertain now may eventually become easy to explain. Patterns invisible to current investigators may become obvious when viewed through decades of additional data. This has happened many times throughout scientific history. Phenomena that once seemed mysterious eventually became routine. Lightning was once deeply misunderstood. Meteors were once considered impossible by some scholars. Even earthquakes remained poorly understood for much of human history. As observation technology improved, understanding followed. There is every reason to believe the same process will continue. Future scientists may classify atmospheric booms with a level of confidence that seems extraordinary by modern standards. They may identify subtle signatures invisible to current instruments. They may reconstruct atmospheric conditions with remarkable accuracy. They may solve mysteries that currently remain open. Yet there is another possibility worth considering. Future generations may solve some questions while discovering entirely new ones. This pattern appears throughout the history of science. Every answer reveals additional complexity. Every breakthrough uncovers deeper layers of reality. The more we learn, the more we realize remains unknown. This is not a flaw in science. It is one of its defining characteristics. Knowledge expands, but so does the horizon of mystery. The East Coast booms sit within this ongoing process. They are not merely isolated events. They are data points in a much larger story about humanity's effort to understand the world. Future investigators may revisit these events using methods unavailable today. They may reach conclusions that seem obvious in hindsight, or they may discover aspects of the mystery that we have not yet considered. Either way, the investigation continues, because science is not a collection of final answers. It is a conversation extending across generations. Each generation inherits questions from the previous one, contributes new observations, and passes an expanded understanding forward. The East Coast booms are now part of that inheritance. A small but fascinating chapter in humanity's ongoing attempt to understand the atmosphere, the planet, and our place within a universe that remains far stranger than we often imagine. In the end, the East Coast booms changed almost nothing. Cities continued functioning. Roads remained crowded. Businesses opened the next morning. Life moved forward exactly as it had before. No major disaster followed. No dramatic revelation emerged. No world-changing discovery suddenly appeared. And yet, in another sense, the events changed everything. They changed the perspective of the people who experienced them. For a brief moment, thousands of individuals were reminded that certainty is often an illusion. A sound arrived from the sky. It interrupted routine. It disrupted assumptions. It forced people to confront a simple but profound reality. There are still things happening in the world that we do not immediately understand. That realization may seem insignificant, but it carries enormous value. Modern life often creates the impression that all important questions have already been answered. We carry devices capable of accessing vast amounts of information. We navigate using satellites. We communicate instantly across continents. We are surrounded by technology so advanced that it can feel almost magical. Yet beneath all of that capability remains a fundamental truth. Humanity is still learning. The atmosphere remains a frontier of discovery. Space remains a frontier of discovery. Even the environment immediately above our heads continues producing surprises. The East Coast booms were reminders of that fact. They demonstrated that mystery has not disappeared from the modern world. It has simply changed form. Instead of existing at the edges of ancient maps, mystery now exists within complex systems that require increasingly sophisticated tools to understand. Atmospheric physics, orbital dynamics, acoustic propagation, remote sensing, data analysis. These are the modern frontiers where uncertainty still lives. And that uncertainty is not something to fear. It is something to appreciate. Because mystery is often the first step toward discovery. Every major scientific breakthrough began with something that did not fit expectation. Something unusual. Something unexplained. Something that forced investigators to ask better questions. Whether the East Coast booms ultimately receive complete explanations or remain partially unresolved, they have already fulfilled an important role. They have reminded us that curiosity remains essential. They have reminded us that observation matters. They have reminded us that science is not merely a collection of facts, but an ongoing process of exploration. Most importantly, they have reminded us that even in an age of extraordinary knowledge, the universe still retains the ability to surprise us. Sometimes that surprise arrives as a distant galaxy captured by a space telescope. Sometimes it arrives as a mysterious signal detected by an observatory. And sometimes it arrives as a sudden boom echoing across the sky, leaving thousands of people asking the same simple question at exactly the same moment. What was that? The fact that we continue asking such questions may be one of the most encouraging signs of all. Tonight's journey began with an explosion, or at least what sounded like one. A powerful boom rolled across parts of the East Coast, shaking windows, startling residents, and triggering an investigation that led us through atmospheric science, satellite observations, meteor detection systems, aviation possibilities, historical sky quakes, and the remarkable complexity of the atmosphere itself. Along the way, we discovered that the story was never really about a single sound. It was about something much larger. It was about how humans respond when reality briefly steps outside our expectations. It was about the relationship between observation and understanding. It was about the delicate boundaries separating what we know from what we are still trying to learn. The East Coast booms remind us that uncertainty is not evidence of failure. It is evidence that investigation is still taking place. Science does not begin with answers. Science begins with questions. Every mystery starts with an observation. Every observation invites curiosity. Every act of curiosity creates the possibility of discovery. In that sense, the booms accomplished something remarkable. They encouraged people to pay attention, to notice the atmosphere, to think about the sky, to wonder how modern monitoring systems work, to appreciate the extraordinary effort involved in transforming observations into understanding. The atmosphere above Earth is not silent. It never has been. Winds move continuously across continents. Meteors arrive from space. Pressure waves travel enormous distances. Storms exchange energy on scales difficult to comprehend. Aircraft cross invisible highways overhead. The sky is active every moment of every day. Most of the time we simply do not notice. Then occasionally, something happens that forces us to look up. A flash. A meteor. Then a roar. An eclipse. A mysterious boom. For a brief moment, our attention returns to the environment surrounding our planet. We remember that we live beneath a vast and dynamic sky connected to an even larger universe. Perhaps that is the most meaningful legacy of the East Coast booms. Not the explanations they may eventually receive, not the headlines they generated, but the reminder they provided. A reminder that the world remains full of questions worth asking. A reminder that curiosity remains one of humanity's greatest strengths. A reminder that even in a century defined by technology, there is still value in pausing, looking upward, and wondering what is happening above us. And as we bring tonight's journey to a close, the sky over the east coast has long since fallen silent. The pressure waves have faded. The reports have slowed. The investigation continues. But somewhere above the planet, meteors are still burning through the atmosphere. Satellites are still watching. Winds are still moving. The universe is still unfolding. And whether we realize it or not, tomorrow may bring another mystery. Until then, thank you for joining me on this journey through one of the most fascinating atmospheric stories in recent memory. And wherever you are listening from tonight, may your skies be calm, your thoughts be peaceful, and your curiosity never stop reaching toward the stars. And now, as tonight's journey comes to an end, the mystery of those distant booms slowly fades back into the vast background of the universe. Somewhere above the Earth, the atmosphere continues its endless motion. Winds flow across continents. Tiny fragments of ancient asteroids continue burning silently in the upper sky. Satellites drift through orbit, watching the planet below. And countless processes continue unfolding beyond human awareness. Most of them will pass unnoticed. A few will capture our attention. And occasionally, one will remind us just how remarkable our world truly is. The explosions heard across the East Coast may eventually receive complete explanations. Or perhaps some details will remain uncertain. But tonight's story was never really about finding a perfect answer. It was about curiosity. It was about the willingness to look up. It was about recognizing that even in an age of extraordinary technology, the universe still retains the power to surprise us. And perhaps that is something worth carrying with us into sleep. Because tomorrow, the atmosphere will continue moving. The Earth will continue turning. The solar system will continue its endless journey around the Milky Way here. And somewhere, another mystery may already be waiting to be discovered. For now, however, there is nothing left to investigate. Nothing left to solve. Only the quiet rhythm of the night, the steady movement of the world beneath the stars, and the comforting reminder that you are part of something far larger than yourself. So wherever you may be listening from tonight, thank you for spending this time with me. Thank you for joining me on another journey through science, mystery, and the universe. If you enjoyed tonight's exploration, don't forget to subscribe to Sleepy Universe and return for future adventures among the countless wonders that surround our world. Until next time, let the noise of the day drift away here. Let your thoughts become lighter. Let your breathing slow. And as the universe continues its silent work above, allow yourself to rest beneath it. Sleep well, and good night.